In this do now, we're really looking to review our exponent rules. So here we have fractions being multiplied, we've got negative exponents. My suggestion would be to get these each to one fraction first and then worry about simplifying from there. So if we're doing 4a to the negative third c times a, multiplying with same bases, we're going to keep the base, add the exponent, which should give us 4a to the negative second power c, because negative 3 plus 1 is negative 2, over 3 times 6 is 18, a to the negative first, c to the negative second times c squared, negative 2 plus 2 is 0, c to the 0 is just 1, and there we are. From here, I would probably swap around so we don't have any negative exponents anymore, making that 4ac over 18 a squared c, and then reduced. 4 over 18 reduces to 2 over 9, a over a squared, just a in the denominator, and our c's cancel. For number 2, we might notice y to the 0 power, that's just going to be 1. And then that should give us 12 y cubed x to the negative second over the numerator. For the numerator, 3 times 2 is 6, and then we're going to have y to the negative fourth x squared. Again, I like to get those negative exponents in order, so we've got 12 y cubed, and now we're going to bring the y to the negative fourth up. Y cubed times y to the fourth should give us y to the seventh. In our denominator, we should have 6, bringing x to the negative second down. X squared times x squared would be x to the fourth. Now we just have to reduce our coefficients so that we have 2y to the seventh over x to the fourth. Okay. And all of this was really to get us comfortable again with our exponent rules, seeing them with fractions, because today we're going to look at dividing polynomials by a monomial. So you'll notice in each of the 3 examples, we have trinomials in the numerator divided by a monomial in the denominator. Our strategy for this is going to be to separate it out into 3 separate fractions. Because if you remember, one of the ways we were able to add fractions with the same denominator was to say, oh, hey, let's just write that over one single common denominator to make our adding easier, right? So we're essentially going to do that process backwards, taking that one single common denominator and separating it out. Some of you might be looking at the numerator and saying, oh, that numerator is not in standard form. So if you want to rewrite it in standard form, you can. If you don't want to, technically you don't have to, because of the monomial in the denominator, that variable in the denominator, it's not a polynomial either, really. So it's a little wishy-washy there. From here, I'm going to take each term, rewrite it over the common monomial of 3x, and then we can go ahead and just simplify each fraction. So 12x y to the fourth over 3x, that should give us 4y to the fourth, 3x cubed over 3x, the 3's are going to cancel, x cubed over x would be x squared, and then negative 9xy over 3x should give us 3y. Okay. And we see our final answer, which is a polynomial, is in standard form, so it was nice that we reordered from the beginning. Okay. Some of you might be asking, do we have to rewrite into 3 separate fractions? No. If you know you can do the denominator dividing by the monomial and do that simplifying for all 3, go for it. Some students need to see it out in 3 separate fractions to make sure they're doing it correctly. Okay. So that's what I'm going to model. So our second one, again, I'm going to write it out into our 3 separate fractions. And our first one here, as we simplify, we should get xy cubed over 2. So still a fraction, which is fine. If you wanted to write that 1/2 xy cubed, also fine. Plus 2y squared minus, and now here the x's and y's are going to cancel, so we just have minus 1/2. So we really just need to get comfortable seeing sort of these different expressions we can get, some with denominators, some whole, some just constant fractions. It's all fine. And our last one here, maybe a little bit more involved with our exponents and our coefficients. So for our first fraction, negative 9x to the 6 y squared over 3x squared y, we should get negative 3x to the 4th y, and then plus 7x squared. Now don't forget that y didn't cancel with anything, so it's still going to be in the denominator, minus 35 over 3. 3 doesn't go into 35, so we're still going to have that fraction. The x squareds cancel, and we have the y in the denominator, so I'm going to write this as negative 35 over 3y. Okay? And that would be our final answer, and this final answer would not be a polynomial because of the y's in the denominator. Okay? So that was a short little lesson. So now we're going to take the next few minutes to just work on the next page before moving on. Okay. So now that we're comfortable dividing a polynomial by a monomial, we're going to look to apply our polynomial skills into a word problem. So we have the width of a rectangular painting is 3 inches more than twice the height. A frame that is 2.5 inches wide goes around the painting. Write an expression for the area of the painting. Write an expression for the combined area of the painting and the frame. What is the area of the frame? So I would think to just visually model this for myself, and if I do that, I'm going to have a larger rectangle for the frame and a smaller inside rectangle representing whatever the painting might be. So maybe there's just a little face in there. Okay, so the width of the rectangular painting is 3 inches more than twice the height. So this is where we're kind of going with let statements here, and I'm just going to model it in the picture. The width of a rectangular painting is 3 inches more than twice the height. So that would mean our height of our painting is x. The width is 3 inches more than twice the height. So that would be 2x plus 3 for our actual painting. Then we're told that a frame that is 2.5 inches wide goes around the painting. So that 2.5 inches is talking about the thickness of the frame. So that means from here to here is an extra 2.5 inches. From here to here is an extra 2.5 inches. Here to here is 2.5 inches. And here to here is 2.5 inches. So if we look at that, we should notice that both the height is going to get 2.5 inches added, or a total of 5 inches, and the width is going to get 2.5 inches added, or a total of 5 inches, making our height, right, which would go from here to here, x plus 5, and our width, which would go from here to here, 2x plus 3 plus 5, oops, or just 2x plus 8 if we simplify it. Okay. Now I feel ready to tackle A, B, and C. Write an expression for the area of the painting. So the area of our painting, we're just talking about this little rectangle with the smiley face. Area is length times width. It's a rectangle. So that would be x times 2x plus 3. And then we can simplify that, making that 2x squared plus 3x. And if we wanted to put units, we would put inches squared. Okay. write an expression for the combined area of the painting and the frame. Here we want to notice that when we outlined the height and width of the frame, that's just a larger rectangle, which includes the picture itself. So we can just use what we have in red there, what we denoted as the dimensions of the frame. So there we're going to have a nice binomial multiplication, x plus 5 times 2x plus 8, which then we can go ahead and distribute, getting 2x squared plus 8x plus 10x plus 40, which will then simplify to 2x squared plus 18x plus 40 inches squared. And then the last part, what is the area of the frame? So that's just talking about the frame that's outside of the picture. To do that, we'd want to take the area of the larger rectangle, subtract the area of the smaller rectangle of the painting. So that's where we're going to do 2x squared plus 18x plus 40 minus 2x squared plus 3x, distribute our negative. And combine our like terms. Our 2x squareds cancel, and we should get 15x plus 40 inches squared as our answer. A lot of the problems we have to practice have some really nice geometry applications. If you don't recall a formula for a diagram, just look it up, Google it if it's not given to you. Okay? Although I think most of them are pretty common sense.